So we will start with introduction to Ansys. So as we know, and it is a leader simulation market for 50 years, Ansys, and we have like #1 simulation in all over the world. We have no competitor near around it, and we are like 2 times more faster. And customer have very satisfaction. Like if you see the global rating in 2020, they have satisfied rating as 89%. And Ansys have the employees 48,000 around globally, and they have also channel partner where engineers do simulation, lot of simulation, and help our engineers to do simulation better to make our environment comfortable. So like you have seen, day by day our technology are increasing. So Ansys provide a platform where engineers can do simulation very perfectly with accuracy. Ansys is like a market leader across all the physics. It's not even like particular to one field. It's a leader in all physics like electrical, mechanical. We have the platform. It provides you platform for every engineers, for researchers, for scientists. It provide a platform for, and it have the material information all about components, electrical components, structure. So we have the platform and we have the material in Ansys, and then we can do simulation based on our requirement. So if it have the different module breeds like fluid, structure, electromagnetics, semiconductor, power, and where we have different module which we can simulate based on our requirement, but in particular field. If we discuss about the like fluid domain, basically we have a lot of scopes. Majorly what we do in fluids, we do thermal management system like fluid in flow pipe, mixing of fluids like that, and then we have multi-phase flow and fluid structure interaction. In structure we can simulate vibration optimization, we can optimize our design, we can check our strength analysis, fatigue analysis, thermal analysis, durability. So Ansys offer a like true simulation platform in all major physics sectors: fluid, structure, electromagnetics, optics. Similarly, we have for electromagnetics, we can do simulation for antennas, RF, microwave. We can go for motors cooling. Like nowadays, we can see that motors are developing, and we can do simulation for structure as well as for electromagnetics also. Similarly, we have other tool also for optics, semiconductor, and software and degenerative, where we can simulate perfectly and check our result with practical result also. So these are the world-class companies leveraging our platform Ansys. If you see in aerospace sector, we have Airbus and Lufthansa, so Turbopac. Similarly, in other sector, oil and gas sector, semiconductor sector, we have different companies which are using Ansys product, and they have more reliability on Ansys. So Ansys is giving the reliability to the companies, and the customer is taking reliability from the company. So it's like maintaining the decorum in the society. If we come to academic part, so all major institute of like government institute, tier 1, tier 2 colleges, IITs, all uses Ansys platform, and they are using Ansys products. So when you go for any internship or any for like exchange program, you will see that Ansys is all over the colleges. These are some colleges of top IITs: IIT Delhi, IIT Mumbai, IIT Roorkee. And if we come to like for West partial worldwide college, so these are the list where you can see there are a lot of colleges which use Ansys platform to do their simulation, to do their research work. Delhi House University is like for especially famous for multi-phase flow. It is like in France. So we have like Ansys capabilities in all over the world. If we come to fluid domain only, as we are discussing for CFD, so we have like basic process technology. We do meshing, geometry, then we go for meshing, and then we go for solar, and then post-processing. So they basically there are 3 process in CFD: pre-process, process, and post-processing. So in pre-process we go for geometry modeling, CAD. Just like CAD, we have other CAD tools, CATIA, UGNX. So we can import that file, we can start work on that, or we can create our design itself in geometry, space claim, or design modeler. After that, we have meshing tool, workbench meshing, where we can do meshing for structure, thermal, CFD, we have different physics there. And nowadays, like recently, Fluent have added Fluent meshing in itself, so we can, it is like more robust, and it will save like simulation time because it is not generating that number of nodes as compared to workbench meshing. If we talk about compressor, like turbines, there we have specialized tool for turbines, TurboGrid, where we do meshing in TurboGrid tools. And for research and area, for better control aerodynamics application, we have ICM CFD. Similarly, we have solver for their particular physics, just like for Fluent, we have Fluent solver for CFD. And for turbines, we have done meshing in TurboGrid, we can solve using CFX solver. Similarly, we have Chemkin software for combustion and FNUP ice, like to check the ice phenomena when plane fly at high altitude and like in cold regions. So we have specific solver for particular application. Similarly, we have Polyflow for plastic deformation, or when plastic melt, how it will flow in the die, that we can check using Polyflow solver. So we have discussed geometry, meshing, and based on the solver we do. So once we solve, there is a region, but why we are solving. So we need to get results, like whether we have to check pressure, velocity, their phase transition, solid or modification, so that we can check in post-processing tool. So we have different post-processor tool. Majorly common use is inside CFD post, where we can check our streamlines, flow, pressure, velocity graph. So after post-processing, we can optimize our design also. Like there is Ansys provided tool where we can do optimize our design, and we can sometimes we use like their basic equation for CFD, just like Navier-Stokes equation. After that, we can give our equation or also input using Ansys customization suite. So suppose we are solving for a car. So in car, we have seen like their batteries are also there, aerodynamic system is there, heat radiator are there. So all these things we can simulate separately, and we can integrate them also to check the system level. So Ansys Workbench provide multiphysics integration also. As we know, like CFD, we have Ansys Fluent, world most powerful journal for CFD. You can see in this picture. So here plane design, internal flow, external flow we can simulate. For Ansys CFX, we have turbo machinery part, mostly in Navy application. If you see in dam civil also, like we can have for civil, they decide the dam structure, and based on dam water flow, we can design our turbines blade to generate electricity. Similarly, we have for plastic sector, we can decide the plastic deformation die. If we come to like simulation platform, so as I mentioned, like for car, this is like one example. In car, we have both things: fluid, structure, electronics, semiconductor, embedded software. So it's like multi-physics domain, and which we can integrate with system level, and we can simulate. So if we can check for aerodynamics, structure, we can check for how the sudden impact or and it will impact. And in electronics, please mute your mic, audience. Hello. So in electronics, we can simulate our signal system, electronic chips.
Muted. Just please unmute yourself. Rohit, please.
No,
Rohit,
sir.
please unmute
One
yourself.
webinar is there.
So 11:30, no, sir? 11 o'clock only. Someone told 11:30? Oh, yeah.
So I was not audible till now. Hello.
It's not audible.
Now it's audible.
Yes, audible.
Okay, I will start. Sorry, I thought I was audible.
No, you have to start from the beginning. I think
No,
it was
you-
4th to 5th slide.
Go to the next slide, Rohit. You are go to the next. Next.
Next one.
Next. Yeah, here. Up to you can
Yeah,
start
here.
from here.
Yes. So as we know that Ansys have the it's provide a platform for multiphysics also. So we will discuss about the electronic vehicles. Just this is some example I am taken for automobile. So in automobile you can see we check for aerodynamics to reduce drag of our vehicle. Then we have structure analysis to impact analysis. This is like for battery I have shown when the car get accident how will it impact on the batteries. So we can check for structural analysis also. And electronics we can check for the electronic system how the current will flow, and this thing simulation we can do is their radiation like car antenna we have that we can check in electronics. Semiconductor we have chips, so based on we have audio system there, so behind audio system and display we have chips, we can do their simulation, can check thermal management of their chips. Similarly, in embedded software, we have signal system. So all these have different multiphysics, and we can integrate this multiphysics in one system, and we can simulate overall the performance of our automobiles. So Ansys provide this platform where you can do multiphysics and can combine and can check for overall system. So this is like fluid. I have taken one more example in which we are doing CFD simulation for batteries. Structure we are checking for the chassis, how it will impact in chassis. Like vibration analysis we can do, model frequency analysis we can do. So similarly we have a lot of scope in structure also for batteries. In electronics we do simulation for motors, electronic motor. Because of better electronic design motor we can get more energy from motor. Similarly, in semiconductor, we have tools we can do simulation and embedded software as discussed. So like this, we can simulate our battery problems related to automobiles, and we can have better battery design. Now, if we come to battery, we all have seen like battery in our homes, in our cars. So the basic phenomena of battery is like it is a part of single unit cell. A cell is a single unit device that convert chemical energy into electrical energy. So basically what battery cell do, they just convert their chemical energy into electrical energy. So when we collect this number of like cells and make their arrangement in series or parallel, it is called as batteries. So batteries are the collection of one or more cell whose chemical reaction create a flow of electrons in a circuit. If you see in this figure, these are the from electrode level we have, and this is the level. So electrode level is the define how electrochemistry will work, how electrons are flowing. We have studied in chemistry also. After that we have cell level where we check for discharging. So there are two types of cells, batteries, like primary and secondary battery. Some cells you can see, you put in sunlight, you can charge it, they get charged. And similarly we have some batteries in our home, after electricity comes we can charge it. So there are two types of battery, primary and secondary batteries. Primary batteries are single use, we cannot charge them, but they give like more energy at one time. And secondary batteries are those batteries like which we can recharge. Similarly, after joining these batteries, we can create a pack level in series or anything. So there we can do like thermal management, battery management system, safety we can check, and we can check the durability also, like life of battery. So this thing we can simulate and pack based on our requirement. Like from car to we have different requirement, and automobiles we have different requirement. So we can pack based on our requirement. Then we can go for system integration, just like I have shown in last slide. We can do system integration also. So this is the basic principle. I think everyone is aware of this, how electrons flow from anode to cathode. And this is the electrolyte where electrolyte is the major, and current flow, like electron flow from high potential to low potential direction flow. So battery have two nodes at anode and cathode. So basically when electrons flow from anode to cathode, current chemical energy is converted into electrical energy. So their development process, stack of cells we can connect in series, and we can have like for like batteries, there is a development. So we can develop a process. Just we have to stack the cells. We have to connect them in series or parallel. Then we have to design a better cooling system. So because when current flow, they generate a lot of heat. So we have to design a cooling system also. And after cooling system also, we have to manage other things also, not even like battery only. We have to manage lot. We have to check lot of factor also, I will explain in later how we can do management of batteries. Then we will put a casing around it so that it not harm, like it will not leak any acid or something, because some batteries have acid around it. So these are basically most of cell types. We have cylindrical cells, as you have seen in your remote cells. We have cylindrical type of cells. Then there are prismatic cells. These are mostly used in like defense sector, and pouch cells also. They are mostly used in defense sector. So when soldiers can go to like their practice area or across the border, they have navigation control unit. So they use some batteries there. This type of some batteries are prismatic and pouch batteries. And if we see about application in other industry, aerospace, transportation, all over the application, we have batteries nowadays, because everything runs on battery. And since the technology emerging and we don't have that much renewable resources, are very left few, so we are moving towards batteries. So if you see here in home, we have batteries, luminous battery, and nowadays in electric train are also running by batteries. They have, you can see in this figure, we have more batteries. So this is multiple stack battery, and this is like single cell for alarm. So we can feel that in day to day our life, we have batteries around us. Earlier these petrol cars were like in production sector, in mechanical sector, they used to go with diesel. Now they are changing with electrical batteries. So we have application in aerospace, transportation, consumer electronics, oil and gas. I will show you one more example here. If you see the use of like from starting aerospace sector, like in aeroplane, we charge our batteries to start the engine itself. So we have batteries there, and when the like sometimes engine fails, the plane fly on batteries backup. So there is very importance of battery in major sectors like aerospace and defense. If you see here on down figure, these are the like they send missiles. So but if you go to warfield, you cannot have like electricity. So we have generator there, and generator have the batteries backup also. So earlier they used to go for generator. Now we have battery system also for aerospace and defense sector. In this also, these people, army soldiers are navigating with the help of batteries. So battery have very importance in our life. If we see from like in transportation sector, everything we see have batteries, because nowadays you can see electric buses are running. It is reducing our pollution level also. So battery have very huge impact. They are running on electricity. So the change of chemical energy to electrical energy is used here. And somewhere we get energy from power plants. So these like chips devices we have, they have battery cells also, and they work on batteries also. If we go to healthcare sector, where batteries are very crucial, because they can maintain our health, they can save our life, because some during operation time we should have that much backup, and that backup is like on batteries, inverters, so that doctor can do their surgery without any hesitation, without any tension. Similarly, in batteries have major roles in the aerospace sector and health sector. We cannot neglect them. Nowadays, if we come to challenge, you have seen like cars are burning, and this is a, like you have seen the news where the man fire that scooter itself, because this is reason. If we don't not manage batteries, if we don't see the batteries levels, then it can lead to disaster, like hazards also, and disaster. So challenges are batteries are not that simple. It looks very simple that we have single cell and we module, but batteries are multi-scale and multi-domain by nature. They have multi-physics. So we have electrochemical reaction, then we have to manage thermally also, and they are multi-scale and multi-domain. Then we have to, their main important is challenge is thermal reliability. How we can rely them on with respect to thermally, because they get heat. You have seen like mobile phones are burning when during charging. So we have thermal reliability is the major challenges in for engineers. We have to manage each battery with respect to thermal. We have to see. Then there are wide range of ambient condition drive cycles. So when battery gets charged and discharged, they have cycles like so their dry cycle, they are known as dry cycle. So in automobiles, when we accelerate pedals, so there is cycle in batteries which take energy, and then when we remove pedal, it store some energy. So these are the cycles. So if we vary there are a lot of variation, it change the impact on batteries life. So we have these are the challenge how we can manage them. Similarly, we have safety and structural integrity, and the whole car influence system. It's not like if we design battery and if we left other system like motor and other things, that will also impact on our battery. So we have to think of all over the system of car, and then we can have better design. So, and which software we have to use. So now till now, I think most of people don't know how we can simulate battery and how we can do multiphysics of all electronic vehicles. So Ansys provide this platform, and we can simulate using Ansys tool. Now I will show you how we can model in Ansys. So there are some module which can simulate. If you are aware of like Ansys Fluent, it is a robust solver for CFD problems. We have like different modules for multi-phase energy. If we want to go for thermal, we go for energy. So we have viscous laminar model for like flow for laminar and turbulent model. This like we have added one battery model in Ansys Fluent itself. So you can simulate, turn on this model, and you can have different method. So once you turn on this battery model, you will find there are 4 methods of simulation: conjugate heat transfer coupling method, FMU method, conjugate heat coupling method, circuit network solution method, and MS multi-scale multi-domain method. So out of these 4 methods, we have like subsystem also, like some option will come on for electrochemical chemistry, like there's working on electrochemistry also. So if we have study in chemical, we have seen electrochemistry. So in electrochemistry, we have 4 models which give like more accuracy. So we can solve, we have 4 methods, and we can solve using electrochemistry. We have 3 methods, and we can define our electronic model also. Like Ansys provide you this leverage that you can use your electrochemistry model also. If we come to Cst coupling method, it's a conjugate heat transfer coupling method, the simplest solution method. In this, the heat generation rate is, we know, like when we are doing simulation, we should know what input we have and what we have to get. So in Cst coupling method, we have basically the heat generation rate, how much heat generation rate will be there. Then we will do the thermal analysis. Then heat source energy equation is specified explicitly. We will use Joule heating in passive conductive zones and inducing battery zone. So if we come to here, conductive zones and active zones. So this is the region. These are on top, we have tabs. These are passive zones, and bottom where electrolyte is there, this is known as active zone, like where our electrochemistry will take place. So in this method, a single potential equation is solved in potential zone to obtain Joule heating, and this is the equation we use for this. If we turn on Cst coupling method, you can see this is not electrochemical level. This is like just simple level. So for electrochemistry, if we go to previous slide, this option comes in MS multi-scale, multi-domain, and circuit network method. For first two method, we don't have electrochemistry models. We have direct method because their equation are very simple. We can simulate very fast. Similarly, if it comes to FMU Cst coupling method, so sometimes what happens, like manufacturer, they give their own electrochemistry models. So there we have to provide like heat generation rate based on their requirement. So in second method, we give like it is by importing into Ansys Fluent. So similarly, we can have Joule heating included, and there's equation similarly as Cst. The major difference between previous equation is that here we know the heat generation rate, we can give as our like experimental data. But in suppose if we have don't data and customer, like some manufacturer want that for this particular heat generation rate we want to check, then we can use FMU Cst coupling method. Similarly, then we have circuit network method. It will define like how the circuit network, just like in electrical, you have seen how the resistance capacitors are there. So this is the like network method. So in circuit network method, every battery is treated as an electric circuit and a battery pack is treated as electric network. So we study the behavior of battery, including current, how the current and voltage are distributed in full network system, and how the heat generation rate will be in each battery will be obtained. So we can have multiple batteries here, and we can check and we can create a network, and we can see how network we can create. So in heat generation with battery is assumed to be uniform. In this, there are some assumption. When we go for any simulation, we will assume some assumption. So these assumption in this method, we assume that heat generation is uniform, and therefore total heat for each battery is distributed uniformly within active zone. So in this case, we will use uniform heat generation. So the Joule heating effect within battery passive zones can be optionally included in the simulation. So as you remember, I have told you earlier also, this is the passive active zone and these types are passive zones. So you can imagine how equations are solving in their particular zones. And this is the most multiphysics solution method where we have, when we put in series and parallel, we mostly go by MSMD method. So this is the, because of Li-ion battery are very difficult to model, and they have multi-domain multiphysics nature. So we have MSMD method for lithium-ion batteries, which have like different length scale associated with different physics. So lithium-ion batteries are very complicated in nature. They have multi-scale, multi-domain, and we have to check for the more equation to get battery thermal electric field and how the current density is there. So these things we can model using MSMD solution method. If we come to basic like geometry, we can create geometry. Here you can see we have created one single cells and we have arranged them in series. So this is a stack of cells, and we can model. Ansys have the inbuilt their model library where you can model battery itself and you can work on them. So if we see this package, we have pack of 12 modules, and each module has 14 in series and 1 in parallel. So we can connect in series and parallel configuration using like model tool in Fluent. So basically mesh type is polyhedra, and you can see the mesh size is very high because the thickness of these batteries are very thin. They are very thin, so it's difficult for other tool to mesh them. But in Ansys Fluent meshing, we can easily mesh them. So these are some results contour plots where we have checked the like temperature for Joule heating, how the temperature is in battery when current flow, and these are the current density magnitude. So where the current have the maximum values. This is example of single battery cells, just like I have told, like they're prismatics. This is prismatic, this is cylindrical. So we can simulate for different type of cells also. You can model them, you can mesh, and you can simulate them. So in this, they are showing the current density, and we can check with respect to maximum their static times with respect to time. So we can do transient simulation as well as steady simulation. These are the, like we can pack them. These are the series, 1 in parallel, 3 in series. Second one is 2 batteries in parallel and 2 are in series. So based on your model, we can pack them. And this is like 1 in parallel and 21 in series. So these are in series and 1 in parallel. So you see here, so these are the, we can check their battery analysis. So this is like when I was discussing about a single battery. Now when we have the system battery, we like cells are packed and they are do simulation. So we can simulate for the complete battery pack using Ansys tool. These are further more example which we can do, like these are the contours which we can get from Ansys, like from battery, how to ohmic heat generation, total heat generation, temperature, current vector plots. So these helps us to decide the battery electrochemistry, how the current is flowing, so how ions are transforming. Let's see ECM model. Please let me know if your video voice is coming or not.
In this video, I'll show you how to use the Ansys Fluent
Are you audible? Like voice is audible?
Yes, audible.
Video voice.
Scale multidimensional or MSMD battery model to simulate
Yes, it's
electrochemical
audible.
behavior of a
Okay.
single cell battery.
So in
The
this,
battery geometry consists of a cell and positive and negative tabs. A battery cell is modeled as an active zone, while battery tabs are modeled as passive zones. Electrochemical reactions occur only in the active zones. The potential field is solved in both active and passive zones. To start, I'll load an MSMD battery add-on using the text command interface. I'll enter 8 to load the dual potential MS.
so this is the older version where like we have the battery module which were used to start using text command in console window. Now we have direct option to turn on battery.
MD battery model. Once the add-on is loaded, the MSMD battery model appears in the tree. Next, I'll enable the transient solver and the energy equation. Then I'll enable the MSMD battery model. In the Model Options tab, I'll select Equivalent Circuit Model and define the electric load type and specify C rate. To specify the coefficients for the ECM model equations in the Model Parameters tab, I'll use the Parameter Estimation tool, which is available in the text user interface. This tool computes the model coefficients from the experimental data. But before using the tool, I'll set values for initial state of charge and reference capacity based on the experimental data. For the ECM model, at least 2 data files are required for different SOC levels. The file format is displayed in the Fluent console. The first 2 lines are state of charge and pulse current information, followed by the time voltage sequence. Once I enter the file names, Fluent automatically computes the coefficients and passes them to the MSMD battery model dialog box. In the Conductive Zones tab, I'll specify the active and tab zones. In the Electric Contacts tab, I'll select the battery's negative and positive tabs. Fluent will automatically apply the necessary current and voltage boundary conditions. I'll verify that the connection information is correct by printing and reviewing it in the console, and close the battery dialog box. Next, I'll define the UDS diffusivity of cell and tab materials. I'll create a new material for a cell, specify its properties, and define the UDS diffusivity on a per scalar basis. This is the method for defining the UDS diffusivity for active materials. Fluent uses these 2 UDS diffusivities as electric conductivity in the 2 potential equations. UDS 0 defines electric conductivity in the positive electrode, and UDS 1 defines electric conductivity in the negative electrode. I'll specify diffusion coefficients for both scalars. For the active material, the electric conductivity is not used. For positive and negative tabs, I'll create a material by modifying copper that I've copied from the Fluent Materials database. The tab zone is passive, and the UDS diffusivity for the tab material must be defined through this user-defined function provided by Ansys Fluent. For passive materials, I also need to specify electrical conductivity. Next, I'll assign the active material to the cell zone. And the passive material to the tab zones. I'll define the thermal boundary conditions on the walls, turn off the flow equation, remove the convergence criteria, and initialize the problem. I'll set the time step size to 30 seconds and run the case for 50 time steps. Once the simulation is complete, I can visualize the results. I can select from a variety of battery post-processing variables that are available under the user-defined scalars and user-defined memory categories. For example, I can display the contours of phase potential for the positive electrode. And for the negative electrode. Or I can display the vector plot of current. Now I will return to the battery model setup and show how to speed up the simulation with no loss of accuracy using the reduced order method. This method can be used if the battery electric conductivity does not depend on temperature, and the electrochemical reaction can be assumed to be uniform over a battery active zone, which is usually a good assumption. To efficiently use this option, we need to have reference potential fields as a starting point for the domain. We can obtain them by solving the problem for only several time steps using the direct method. Then we can switch the solver to the reduced order method and continue the simulation. I'll reinitialize the problem and then run the simulation for 3 time steps. Now I can enable the reduced order method and continue running the simulation for the remaining 47 time steps. The reduced order method solutions are time efficient and produce results that are almost the same as in the direct solutions, but we are not solving 2 potential equations, thus saving a lot of computational cost. This concludes the demonstration of using the MSMD battery model for a battery cell simulation in Fluent.
I hope everyone got idea. So basic thing is like you have heard of SOC, state of charge term. So it is the measurement of amount of energy available in the battery at a specific point in the time expressed as percentage. So every battery, when they charge or discharge, they have some specific charge. Like this data we'll get from experimental data, or we can assume something, and we can get from the customer also at this charge. Then we will positive types and negative active zones, and we will define diffusion, and then we will simulate. So in last you have seen that they have used reduced order model. So that is like efficient method. After giving some iteration, we can go for reduced order method, and we can simulate very fast. So I hope this give you more idea. So there are certain phenomena also which we can simulate in simulation. So if these are like external and internal short circuit treatment, so you have seen like most of time our battery gets short circuit, even the cells get collapsed, and so we can study in Ansys itself how we can create that phenomena, short circuit treatment. So Ansys Fluent battery model can handle both external and internal short circuits. These are very important to study so that we can have better battery design. In case of external short battery positive negative types are connected directly with no electric load. So you have seen then we were assigning some properties to the types as well as to the negative types. So we can assign properties directly with battery positive types and negative types, and we can check for the short circuit treatment. So in case of internal short circuit, like we can, like it happens mostly due to crash. So you have seen like when electric car get accident, their battery can, in this figure if you see, this is just a 4 single cells I'm saying. If in real impact, if we see big cars, they can impact and can create short circuit also internal. That's why car get fired. Even sometimes we have seen when car get accident, they generally get fire. So because of short circuit in batteries. So this will give you more like view how when it impact on battery. So this is the thermal abuse model. We can go for simulation for thermal abuse model also in Ansys Fluent, where we can predict how if a car hit by this much and how it will impact on the batteries, how leakage will be there, smoke can come out, gas venting. So these studies we can do. Ansys Fluent offer 2 method in this for thermal abuse, 1 equation model and 4 equation model. Thermal run equation are very complicated and material specific, so you should have proper details while going for thermal abuse model simulation. So these are the like I have captured one in MSP battery model, where we can go for advanced model, thermal abuse model. So there are models in which we have some models, and based on requirement we can go for some model also. If we want to go for thermal abuse model, we can check here. We in MSMD model we can go for thermal abuse model, where we have 1 equation model and we have 4 equations. So these are the 4 equations we can use, and this is one equation model, and this can be run without a electrochemistry model also. So this is the advantage, we can simulate very fast for thermal abuse model also. If we come to battery management system, so this is like how we can manage our battery to save battery from sudden failures, these things, functional safety. So what are the advantages of battery system? So main function of battery management system is that for I'm talking about only electrical. So we have different field which have different management system for related to their particular. If we talk about electric vehicles, because nowadays you can see we have electric vehicles are coming over days. Earlier bus came, now cars are coming, bikes already came in market. So after some years you can see all diesel cars and petrol cars, they will be replaced by batteries. So we should have that reliability on simulation, because if we do simulation before going for real, it will save a lot of cost and time. And by doing simulation also we have to manage that battery also. So Ansys provide this tool also. So if we go for advantages, we can have better function, because if battery operates properly, other component will function properly, and lifespan also, and reliability. So we can predict the life of battery also, how long it will run. So you have seen, like when you go to market, people are saying that this battery warranty is up to 5 years. How they are saying that? Because they know, they have check their simulation in that this with this much charge and this much load, it will take this much time to totally discharge. So like that we have model for lifespan, and we can check for that. And similarly we can check for the cycles where it performance vary with respect to each cycles. So when you drive vehicles at low speed, it will not consume that much petrol. Similarly, when it's related with battery also, when you run with constant speed, you will have more better efficiency. It will increase your battery performance. If you have variation in speed, sometimes 40, 20, suddenly 80, 100, so it will impact on battery. So we have to manage that thing, because all people don't know driving, but some people, because they are new to the driving, so they might not, so it will impact their car life and similarly battery life. So we have to increase the performance of battery, so that we, if there are some sudden loads, it can bear that loads also. And there is like last is like cost and warranty reduction. So you have seen like cost is we have to reduce, because our, if we have more cost, nobody will buy the electric vehicle. So this is like research is going on how we can reduce cost and reduce the warranty. Apart from like other simulation, we have for battery, we can go for structural simulation also. Like this is like for management system. So if we manage the electric motor, it will save battery also. So as I think everyone is aware of the structural analysis, where we do stress analysis and fatigue analysis. So this is the domain where we can go for electric motor simulation, and we can take data and interpret that in system level. So if we talk about battery management system, it's about total management, full system level, not about only batteries, because we did simulation in battery. Now we have to manage full for all of the system. So other system impact will also take place. So structure, we have this multiphysics solution, mechanical, where we go for model analysis, frequencies, mode shapes. In harmonic analysis, we go for full and model, super harmonic analysis, damping. So we have different simulation for particular application, and you can do all multiphysics using Ansys tool in one single platform, that is Ansys Workbench. So these are the vibration analysis. You can also check on gear system, because when the motor goes, it will transfer the energy, and there are teeth, gear teeth, which will impact. So we can check this also, how it is impacting. And if we have proper gear system and vibration analysis, we have proper, then we can control the energy transfer from battery to vehicle. So there are some standards on which battery we do like some design optimized for thermal stress conditions as per SAE standards. So these are the standards they have maintained. Battery drop test we can also do using Ansys Workbench. Then we have nail penetration test, Cst test, and impact test. So these are the simulations which we can do using Ansys Workbench for structure, thermal, all this. So similarly, we can check for cell performance. What will the impact if we can create this phenomena? It's one is like practical. If you go for practical, it will create a lot of cost. And but in simulation, we can do in very fast and we can predict and we can validate also with one result. Then we can have more design. Similarly, we can do simulation. And this is like battery life model. For battery life model, we have three models: empirical battery life model, battery capacity fate model, and physics battery based model. So as I mentioned, based on repeated discharging and charging cycles, the battery life effects. So we can predict how much it will affect and how long we will have battery. So we have three models. And this is the latest addition in the Ansys 22 version, where we can go for battery swelling model. You have seen like in your mobile phones, your batteries are getting swelling. So we in simulation, we can create that swelling itself, and then we can simulate that deformed configuration, and we can check how the battery life is reducing and how it will impact, how the current density will change. Thermally, we can check. So in video, you have seen that simulation, if we go for Fluent CFD, so it has taken around 3 hours and 12 cores. But if we go with less transient, like field equation, and then we go change to ROM simulation model, it solved within seconds. So we can go for ROM method. So once you get some like hand-on practice on Fluent CFD simulation, then you can go for ROM. You directly cannot jump to ROM method because first you have to practice on basic Fluent. Then you will get some idea how to do simulation. Because reduced order is like highly fidelity dynamic model that preserves essential behavior and domain effect for the purpose of reducing solution time. So we can reduce a lot of computational times using ROM model. So these ROM method like comes in like battery also and battery management also. They will help in for system level also. When we go for system level, we can use RO method also. And these are the like battery model. They are coupled with thermal model. So if you see, this is the Ansys Twin Builder. We have the tool in Ansys itself where we can create an electric network and we can check for the different methods. So they are SVD ROM method and LTI ROM method. So we will have one more webinar on thermal management system where we will discuss about this method in detail. Just I'm giving the overview that we can do thermal management also using Ansys tool. So if you will get more idea from this picture. So when driver picks, so this is a controller which which control our battery motor, and then we can based on controller current will discharge from battery and it will transfer to the tire or transmission unit. So we can simulate this full system level analysis using Ansys Twin Builder or Simplorer. So these are the other perspective view where we can have equivalent circuit, thermal network, we can create equivalent, we can solve for, there are multiple options for simulation. So from some model to unit to group, we can module up to system level. So these are the like some features we will discuss in later webinars when we go for battery management system. We will notify you all people when we will have battery webinar for thermal management. So you can see here we can predict the pack voltage of module cells for driving schedule. So it gives you the values for, we can check for multiple cycles and we can go for simulation instead of going for real model. We can check with, actually this data comes from real model, then we will integrate into Ansys Twin Builder where we'll put same condition and check and how we can improve. So similarly once we have some data, so we'll compare with our simulation setup. So once our simulation setup predicts same values, so means our setup is changed, then we can enhance that models also. So this is the case study, like a GM motor they have done. So they have done for 24 cell module and they have done for cooling system also, like so even Tesla, they have used battery like Ansys also for battery cooling. They have used different models. So if you see here, they have used fin plate and cooling channels. So this is liquid cooling inside battery itself. And this is like one more VWR racer. They have in electric car, racing car, they have simulated for system level. They have managed thermally full system and using Ansys Twin Builder, and by using other tools, they have simulated full batteries power, like full system level. So I will show you one small demo on like single battery cells using multi-scale domain. So this is our workbench where you can see we have a lot of module here. So this is for like analysis system where we have for fluid flow, SafeX for turbines, just I mentioned, and Fluent. This is for polyflow, harmonic. So we have both things, system level as well as component level. If you want to go one by one, we can create geometry, then we can create meshing also, just like we have to do. So I have imported one geometry file and mesh file. So this is our model. If you go to models, we have battery model on. We can enable battery model. Okay, so now you have seen that when we activate this model, so you can see we have 4 models: conjugate heat transfer model, FMU model, circuit network method. So these methods are there. I will go slow by slow so that people can see and can look which option I am clicking on. So we will go for MSMD model as I've discussed. So we will enable Joule heating in active zone also and passive zone also. If you have any doubt, you can ask me here in model. Like then once we have given, we can click on OK. So this is our MSTM model, and electrochemistry model is NTGK empirical model. So they are different model, and I am going with in this demo with NTGK empirical model. We have to click OK. Okay. Now we have to define the conductive zones, material also, cell zones. You can double click on this, then you will get both zones, active zones and passive zones also, and you can elaborate from here also. So you will go for electric zones, you can edit them. Sorry, I have not given material. Yes, here we have the conductive zones. We can go from top side also, where we have conductive zones, electric contacts. So we have to give these inputs first, then we can go downside. I will go for conductive zones. Now you can see here we have active component and passive component. If you go to active component, we have zone, E zone, S. Okay. Again, we can go here. If you have like selected any tabs, you can deselect also here. So I have mentioned like active zones are electrical zone and passive zones are where we have tabs. So we will select tabs here. Now if you will go to electrical contacts, now we have negative tabs is negative tab, and for positive tabs we have positive tab. So just like we can define properties. You can print battery connection information also. It will show you number of batteries in stage 1 and number of batteries in per series stage 1. So since we are using one single cell, so it is showing here. Now we'll go for model parameter. Here we have to define some values. Okay. You can see here parameter function like just like in ECM model we have defined. It is already defined here. So we'll click on OK. Now we'll go for material. So in like CFD or any process solver, this is the basic standard. We go step by step. So first we'll define the general condition, whether it's steady and transient. Then we'll define the models. Then we'll define the materials. So in model we have defined the battery model, and now we'll define for material. So you can see here default material is both fluid and solid, but we are not going for fluid here. We will create one material ourselves for electronic material. So you can click on material, expand. Add it. You can write name here, new material, electronic material. So sometimes when material is not available, you can write down their properties also. I'm changing the density. This is the data like I have taken from one sample. The default values were for aluminum. Now I'm changing this value for electronic material. Now we'll define here UDS. UDS 0 will define constant. We'll define here unit power. Yes. Now you can see the material is changed from aluminum to electronic metal. So we have given the metal properties here. You can click change it, close. Similarly, we'll create for positive type material. Electron, proton. We'll change the properties here. I will define as constant. So you can change any value with respect to like whatever data you have, you can change, you can create your material also. So you have to select like what material type you can have, solid or fluid. So this is we are working for solid, and you can name by chemical formula also. In Fluent database, we have like lot of material which you can use, and you can create by defining also. So in this also we have material type for fluid and solid. So you can based on, you can select, if you want to select for copper, you can select also. So these are the properties of copper. You can copy, you can close it also. You can name it as also, rename, you can rename also them. It's not a big issue. So it is asking whether to create overwrite. Yes, you can create or no. So you should know. Yes. And now close it. Now we go for cell zones. So it's defining where we have cell zones. We can edit even electronics. So now you can see here we have material. Earlier we were having aluminum. So we can define the material here and we can apply. So we'll assign P material for these both zones. Now we'll come for boundary conditions. Now we define the cell zones, active and passive zones. We define the material, which zones we have material. Now we'll define the boundary condition. So if we go to boundaries, we will have to see the walls. So you can see here we have an negative, positive. I will show this. So here we'll define the heat transfer coefficient. So in walls. So we will go for active wall and double click. Now you can see here thermal properties which we can give. So whatever the thermal properties you have, you can give heat transfer coefficient. But here, if you see here, we have to enable convection here. So heat transfer coefficient is enabled using convection. So you should know like which option will come under which type. So convection have heat transfer coefficient. So we'll give heat transfer coefficient value 5. And we can set temperature, fixed temperature is 300 Kelvin. We can apply and we can close it. And there's more option, like we can copy also this material. We go to boundary condition. So we'll copy this whole active. You can see here we have option edit or copy. So we'll select copy. So we'll select copy for volatile. From boundary zone, it is asking. So we'll select. So where we have to copy N vol and positive voles. We have copied it. It is asking yes. We can say yes. So we have defined the material. We have defined the boundary condition for this. I will close it. You can check properties also for this. It will have same properties if you want to see. So now you can see we have copied, and there are two methods. Either we can go there and we can edit, or we can copy. So when we have option of copy, we can go for shortcut also. Similarly, we can check for this also. You have seen we have copied. Now we'll go for solution control. You can go from top also. If you see there are some same option we have, we can have like solution control downside and top side. So if we have to give more equation, we can go for equation. Now you can see we have 5 equation. So we are not going for any flow, not any for any turbulence. So we will deselect them. Now we are simulating for energy, another equation. So click on OK. Now we can check our residual. Just like in that tutorial we have seen, like they have removed the flow equation. We are doing same way. So there is no criteria. I'm selecting none convergence. So I'm selecting none. So basically these are the criteria based on our convergence criteria. So I'm selecting none. If you want to report something, you can create report also, just like new surface report, volume report. So you can see here, just like in our, we can report for mass flow rate, weighted area average, volume flow rate, like for fluid problems. Here we will report for area weighted average for surface. So we have to name also, like you can give your reference name also, and you can, so I'm reporting for voltage. So here you can see pressure variable, but we are solving for battery. Now you can go for battery variables, and you can see for sub option passage on potential have been. So if you click on print to console, it will show here. If you don't check this button, it will not show you. So you have to click on OK. So you have saved one more file. Now you can see this file will come here in solution reports. So you can edit from here also. And you can decide the location also where you want to save. You can monitor also SW report files. So you, like just by saying, so we can report, we can browse any location where you want to save file. I'm saving somewhere. I can rename it as and TGK method we are using dot 1c dot out. So this is the extension for these files, report files. So we can get data for each iteration also, and we can print too also. So this is showing the path specified because I have not saved the project. If you see here, so it will save default in the this trajectory. We can create plot also, like in what axis we want x and y, we can click on that also. So here we have x-axis and we can change it. Plot title, duration, we can change also. Here we have axis, we can define x and y. So you can see some option are inside. So you have to first check which option are available where. So once you have some practice, you can get to know which option are there. So we have to go to axis. We are defining x, y axis and precisions. So for precision, it is asking for, we'll set to plot, and precision we can decrease because it will take more time.
Accreditation in
We'll
the
go
classroom.
for y.
So that is the accreditation part.
We'll go for
Then we
precision.
describe outcome based learning, that OBE, that is the means of implement accreditation in the classroom, and this course also cover the assessment and evaluation, that part also, because that is also an integrated part of accreditation and outcome based education. Without assessment and evaluation, this how do you implement outcome based education in classroom is very difficult. So this course eventually covered three aspects of learning. This whole course is that you will be able to in the classroom, so that I can claim that while I am teaching signal processing, digital signal processing, of that course outcome I achieving, I will demonstrate the software how do you, which I want to develop at the end of the course. So we can check for the maximum temperature also, and the question paper will be MCQ based, and this MCQ
minimum temperature
is
report also.
I'll discuss how to design MCQ question, so that the MCQ question
and
you
we are
cannot
selecting the
find
zones,
none of them, all of them have this kind of choice.
And we are going for static temperature, so you can change the variable here. Now we have created full setup. We can save this file as case setup. So this is like basic phenomena. We can export case. When we have the solution, this option will get on. So case and data. Now we are just case. So we'll save it as case data. And battery can name is 24. So we have saved. Now we initialization. Go to solution, initialization. We'll go for standard initialization. We go to run calculation. Here you can see we have not make it transient, so we'll go for transient from models general. Then only we can give time step things. So we'll give the time step here. $30. Number of time steps 100. Calculate. I have initialized in steady state, that's why it is showing error. So you now we'll go for run again. And now you can see the temperature graph, voltage plot with respect to time. So these information are very critical when we check for like validation with respect to our practical. So you have seen like in this paper we have a lot of graph plots. And this is the like scale residuals. So we are solving for energy equation UDS and 0 1s. We are not going for flow equation. I will stop in between around 50, 60, 70% because of lack of time. I will show you how much it has solved from that only. Or we should wait. Please let me know. If you want to stop, you can stop iteration here also at the time of step size as well as in the iteration. Let's run it, it will run fast. Till that time, I will see the question if we have some question in chat box. I can choose state in that. Okay. Yeah, we'll try to mail this video also. So now we have completed the simulation. Now we'll go for post processing. Like once you have the results, you can save it as using go to file. Now you can see export case and data option is enabled. So we'll save it as, you can write name as 2. So it has the format of case and data. So it will save our result also. So for now we have completed this step, we can go for this one, contours also from this side and from top also if we have both features. Here you have contours, same we have here. So I'm selecting contours. So we are checking for the battery variable. So we'll select battery variable. So you can go for cathode potential where we'll check active wall on active wall. Display. So now you can see on active wall we have the cathode potential. Similarly, we can check for the contours also, different variable. This is cathode potential and we can close it. Similarly, if we have to add, we can add also new. Now we will for anode potential. Same one. So this will show how the at anode and cathode wall is, these are active zones. So potential difference, it is showing the voltage. You can say how much voltage difference. Based on this data, you can have power. Now we can go check for potential also. When we can create one more new battery variable, and we check for passive zone potential. So when we have to check for passive, we have to go for volts. Vol N, volt positive, tab N, tab positive. Display. So now we can check passive zone material. So this is the passive potential. These are the tabs. Just like I mentioned, in active zones we have electrochemical, and passive zones we have this potential. Now we can check for the temperature also. For all this, you can create one more contour. You can go for static temperature. Here you can find like this feature, you can check here totally whatever you want based on your requirement. Sorry, top we have to select temperature. Now we have to check temperature in volts. Now you can see the temperature, how it is varying. In Kelvin, it is showing. You can change unit also in starting and later on also. Now, if we have to see the current density vector, then we have to go for vectors. Now you can click on vectors, new. Now we have to create current density. You can see for like their junction for NP, we will select for current density J and color by battery variables, current magnitude. And now we'll select the volts.